Quadratic inequalities, like quadratic equations, include the square of the variable under consideration. So for example, if we had to solve the quadratic inequality x squared plus x subtract 6 is less than 0, how would we go about that? Well, there's a well-defined method for solving quadratic inequalities. To solve a quadratic inequality, firstly, if necessary, we have to rewrite the inequality with all terms on one side. We then replace the inequality sign with an equality and solve the quadratic equation to find the critical values. We then sketch the parabola associated with the quadratic equation and then use this sketch to solve the quadratic inequality. Now, written like that, these steps are quite vague. Let's go back to our example and put them into practice. So first we're told we have to rearrange the inequality to put all the terms on one side. That's not necessary in this case because we have all the terms on one side with a 0 on the other. So we can move straight on to the next step, which is to rewrite the quadratic inequality as a quadratic equation by replacing the inequality sign with an equality sign. Then we have to solve this quadratic equation. So in this case, I think this is going to factorize, and indeed we can have x plus 3 x subtract 2 is equal to 0. So therefore the values of x are either negative 3 or 2. Now these are what we call the critical values. We are next told that we have to sketch the graph of the parabola y is x squared plus x subtract 6, and this is one of the reasons why we've got hold of these critical values. They are the values of the x-intercepts of this parabola. It has a positive coefficient of x squared, so it's going to have this smiling shape, and that really is all that we need to know about this parabola. Although we would be able to work out the y-intercept and the coordinates of the vertex, they are not necessary to solve the quadratic inequality. All we need to know are the critical values, negative 3 and 2 where it passes through the x-axis, and the general shape of the parabola. The final step then is to use this sketch to solve the quadratic inequality. Well, we are trying to find the places where x squared plus x subtract 6 is less than 0. We need the right-hand side to be less than 0. But if we have just sketched a graph of y equals this quadratic, then the values for which x squared plus x subtract 6 is less than 0 will be the values for which y is less than 0. Looking again at our sketch, that will be all the values of x for which the curve is below the x-axis, y being less than 0. We can visualize these x values by looking at the red line. For every value of x in between negative 3 and 2, the parabola is beneath the x-axis, so the value of y is less than 0. Notice that because we had a strict inequality, less than 0 rather than less than or equal to 0, we will not be including the values negative 3 and 2, just the values in between them. So by consulting our sketch, we can conclude that the solution is every value of x greater than negative 3 and less than 2. Or in set notation, we could say we have values of x where x is greater than negative 3 and less than 2. We have solved our first quadratic inequality. In this example, all of the terms of the quadratic are not on the same side of the equation, so we will have to start off with the first step, which is rearranging so that everything is on one side. Now, it doesn't matter if we subtract the 4 from both sides to get the form that I'm just using, or whether we move the 3x squared and the 11x to the other side. Both are equally valid. I find it's easier to arrange into a form where we have a positive coefficient of x squared, but that's not obligatory. Next step, rewrite the inequality as a quadratic equation by replacing the inequality by an equality. And then try and solve this quadratic equation. I believe this one is going to factorize as well. and indeed it's going to factorise with a positive 4 in this bracket and a negative 1 in that bracket. So therefore the critical values are x is a third and x is negative 4. Again, because we have a positive coefficient of x squared, when we plot the graph of y is 3x squared plus 11x subtract 4, we know it is going to have this general shape and pass through these two x values on the x-axis. The shape of our curve is therefore this. Once again, it is only the shape and the x-intercepts we are interested in. Referring back to our inequality, we are trying to find the values for which 3x squared plus 11x subtract 4 is greater than or equal to 0. So if we are interested where this expression is greater than or equal to 0, that will be the same thing as finding where y is greater than or equal to 0. With respect to our sketch, that means finding the values of x for which the curve is above the x-axis, where y is greater than or equal to 0, so it includes the points where it intercepts the x-axis. These can be visualized by using these red lines, and you'll notice that we have two regions which satisfy this. For every value of x equal to negative 4 or below, the curve is above the x-axis. For every value of x equal to 1/3 or above, the curve is above the x-axis. So this leads us to the solutions. X is less than or equal to negative 4, or x is greater than or equal to 1/3. And we do have to say or, because there is no value of x which satisfies both of those conditions. It cannot be an and. In set notation, we could say that we have values of x where x is less than or equal to negative 4. We have values of x where x is greater than or equal to 1/3. And we must use the union U symbol for things which are in here or things which are in here. Here is an example of simultaneous inequalities, one of which is quadratic, one of which is linear. Just as in simultaneous equations, we have to solve both of the inequalities and then consider the values of x which are satisfied by both. Let's start by solving the quadratic inequality. Again, we will have to do a little bit of rearranging before we get started. Rearranging to x squared, subtract 7x, plus 4 is greater than or equal to 0. Then we will have to try and solve the quadratic equation. X squared subtract 7x plus 4 is 0. Can't see any easy way to factorise that. In fact, let's just have a quick check on its discriminant. Its discriminant is negative 7 squared, subtract 4 times 1 times 4, which is 49, subtract 16, which is 33, which is not a square number, so we will not be able to factorise this. So I think I will solve this one by using the quadratic formula. The values of x are negative b, which is the negative of negative 7, so it is 7, plus or minus the square root of b squared subtract 4ac. Oh, b squared subtract 4ac is the discriminant, which I've just worked out. So that will be the square root of 33 divided by 2 times a, and a is 1. So there we are. Our critical values, therefore, is that x is 7 subtract root 33 over 2, and x is 7 plus root 33 over 2. If we now plot our graph of y is x squared subtract 7x plus 4, we are interested in the places where this is greater than or equal to 0, so we're looking for y values which are greater than or equal to 0. Again, we have a positive coefficient of x squared, so our parabola will look like this. And because we need values of y which are greater than or equal to 0, we will again have two regions which are acceptable. We'll have every x value below 7 subtract root 33 over 2, and every x value above 7 plus root 33 over 2, inclusive of those critical values. So we have a final solution to the quadratic inequality. X is less than or equal to 7 subtract root 33 over 2, or x is greater than or equal to 7 plus root 33 over 2. Now let's consider the linear inequality. Let's start by expanding the brackets on both sides. So we have 4x plus 2 is greater than 12, subtract 6 plus 3x. Now if I subtract 3x from both sides, I will just have a single x here. If I subtract 2 from both sides, I'll have 12, subtract 6 is 6, subtract another 2 is 4. The solution to the linear inequality is x is greater than 4. Now we need to find where both this set of solutions and this set of solutions can occur at the same time. The easiest way for us to visualize this is using our number line. So the solutions to the quadratic inequality can be illustrated by these two lines. All of the values below 7 subtract root 33 over 2, all of the values above 7 plus root 33 over 2, inclusive of those critical values. The solutions to the linear inequality can be represented like this. All of the values greater than 4, not including 4. We can now see that the only place where both of these inequalities happen at the same time are these values illustrated in red. All of the values from 7 plus root 33 over 2 upwards, inclusive of that end value. So therefore our final solution to the simultaneous inequalities is that we have values of x which are greater than or equal to 7 plus root 33 over 2. This example, on the face of it, does not look like a quadratic inequality. We have 3 over x is greater than 4. Well, we might be tempted to go from 3 over x is greater than 4 to multiplying both sides by x to get that 3 is greater than 4x. But that is only going to be true if x is greater than 0, because we know that if we multiply or divide by a number which is less than 0, we have to reverse the direction of the inequality. So we would have that 3 is less than 4x if x is less than 0, and now we realize that this is all getting a little bit complicated. There is an alternative way to solve problems like this. Let us take a different approach. If we go back to starting with 3 over x is greater than 4, we could maintain the direction of the inequality if we know that we're multiplying by something which is positive, and we do not know that x is necessarily positive. However, we do know that x squared will be positive, whatever the value of x is. So if we multiply by x squared, we will get 3x is greater than 4x squareds. And now we have a quadratic inequality. If we rearrange that to 4x squared, subtract 3x is less than 0, we can now begin our usual method. So we have to first try to solve the quadratic equation 4x squared subtract 3x is 0, which is not a particularly tricky one. We can factorize out an x to get x into 4x subtract 3 is 0, and therefore we have critical values of x is 0 and x is 3 over 4. We now have to draw a sketch of y is 4x squared subtract 3x. We know that it's going to have the smiley shape. We know what the intersections with the x-axis are. So that parabola will look like this. Now we are interested for the values where this is less than 0. So we need the values of y which are less than 0, which are the values below the x-axis. So we can illustrate them by this red region. We have all the values of x between our critical values and not including those critical values because we have a strict inequality. So our final set of solutions are x values which are greater than 0 and less than 3/4. Or in set notation, all those values of x which are greater than 0 and less than 3/4.